Hello everyone, it's Miss Maneely, and I'm going to go through the Algebra 2 Quarter 3 Assessment Review Packet with you. I'm going to begin by going over the unit circle. You will be given a blank unit circle for the quarterly assessment. It is the expectation that you can fill this out completely and use that as your guide for the assessment itself. I would not spend a lot of time filling it out, so I would really focus on completing at least the first quadrant, and then if you need to look at other angles or other measures in the unit circle, then you go from there. So if you can fill it out really fast, that's great, but if it takes you a while, then just focus on filling in quadrant 1 and then go ahead and starting your assessment. And if you have to refer back to it, then you can just fill in the pieces that you need. I am going to go through it pretty quickly though. I'm going to start with the degrees. So all of your angle measures in degrees, there's a pattern. We're going to start at 0, and then we're going to add 30, and then 15, and then 15, and then 30, and then 30, and then 15, and then 15, and then 30, and then 30 again, and then 15, and then 15, and then 30. Whoops. So it goes 30, 15, 15, 30. 30, 15, 15, 30. So I'm going to add another 30. That's going to give me 300. Then I'm going to have 315, 330, and then finally I'll be back at 360. So a 360 degree angle is the same thing as a 0 degree angle. And that, again, those are all measures in degrees. Remember, if you have a positive angle, you're going counterclockwise around the unit circle. If I were going, for example, in this direction, this would be a negative 30 degree angle. And there are some problems on the quarterly assessment that refer to negative angles, so just be careful. Let me erase that. All right, so then let's go ahead and deal with our radians. So again, at 0 degrees, that would be 0 pi. And then I'm going to just start by going through with the denominators. So with the denominators, it's going to be 6, 4, 3, 2, and then we go back up. 3, 4, 6, and then this is going to be a whole pi. And then again, I'm going to go 6, 4, 3, 2, and then we go 3, 4, 6. So one thing that I try to remember is that my denominators of 6 are going to be closest to the x-axis. My denominators of 3 are going to be closest to the y-axis. And my pi over 4s, those are my 45 degree angles. They're basically going to cut each quadrant in half. So they're going to correspond to my 45 degree angles. When it comes to the numerators, in quadrant 1, everything is just 1 pi. In quadrant 2, all of my numerators are going to be 1 less than the denominator. So this is going to be a 2 pi over 3. This will be 3 pi over 4. This is going to be 5 pi over 6. And then I have got my pi. In quadrant 3, everything's going to be 1 more. So this is going to be 7 pi over 6, 5 pi over 4, and 4 pi over 3. And then in this one, this will be 3 pi over 2, sorry. And then in quadrant 4, if I double my denominator and subtract 1, that's how I'm going to get to my numerator. So 3 times 2 is 6, so if I subtract 1, this is going to be 5 pi over 3. With my denominator of 4, I double it. 8 minus 1 is 7 pi over 4. And then 6 times 2 is 12. This is going to be 11 pi over 6. And that's going to be 2 pi. So now I have all my radians. And then finally, I'm going to put in all my ordered pairs. And quite honestly, this is where I would just fill in quadrant 1. And then as you're working through the test, if you have to look at like a 5 pi over 4 angle or 300 degree angle, then you can fill out the rest of it. But I wouldn't spend a lot of time because it's basically the same ordered pairs. You're just changing the sign. So I would really focus on the first quadrant. And so at 0 pi, the x-coordinate is 1, my y-coordinate is 0. I can do my 4 corners at least. This would be 0 and 1. Over at pi, it would be negative 1 and 0. And at 3 pi over 2, it would be 0 and negative 1. So that's easy enough to do. All my pi over 4 angles, those are my 45 degree angles. Those are 45, 45, 90. So if you remember the two sides of the triangle that would be created, so if I were to drop an altitude here, the x and the y values are going to be the same length, and so they're going to be the square root of 2 over 2 and the square root of 2 over 2. If I think about my pi over 6, I think about the triangle that's created there, the x value is bigger than my y value. And so that's going to correspond to the square root of 3 over 2 and 1/2. If I switch this to the 60-degree angle, then I'm just flipping my x and my y values. So I have 1/2 and the square root of 3 over 2. All of the other ordered pairs are going to follow the same format. So if I'm looking at 2 pi over 3, any of my pi over 3s are going to start with a 1/2 and then have the square root of 3 over 2. I just have to remember which values are positive and which values are negative. So in quadrant 2, it's my x value that is going to be negative. So in quadrant 2, the cosine is negative and the sine is positive. And then because tangent is just the sine over the cosine, the sine over the cosine, it would be negative as well. So in quadrant 2, this is going to be negative 1/2. This will be a positive square root of 3 over 2. My pi over 4s, again, it's going to be negative square root of 2 over 2, positive square root of 2 over 2. My pi over 6s, it's going to be negative square root of 3 over 2 and positive 1/2. When I drop down to quadrant 3, the cosine and the sine are both negative, but that means that my tangent is going to end up being positive. So in this quadrant, again, my pi over 6 is going to correspond to a square root of 3 over 2, and they're both going to be negative this time, and a negative 1/2. My pi over 4s, that's going to be a negative square root of 2 over 2, and another negative square root of 2 over 2. This is going to be a negative 1/2 and a negative square root of 3 over 2. And then if I jump into quadrant 4, this is where the cosine is positive, but the sine is negative. And since, again, the tangent is the sine over the cosine, since a negative divided by a positive is negative, the tangent is negative there as well. And so my pi over 3s, it's going to be the 1/2, but now my y value is negative, so that's going to be a negative square root of 3 over 2. My pi over 4 is the square root of 2 over 2 and a negative square root of 2 over 2. This is going to be a square root of 3 over 2 and a negative 1/2. And then in quadrant 1, this is the one thing I didn't do. All of my functions are positive. So in terms of the quadrants and which functions are positive and negative, all of the functions are positive in quadrant 1. So we use A to represent that. In quadrant 2, the sine is positive. In quadrant 3, the tangent is positive. And in quadrant 4, the cosine is the only function that's positive. So if you remember the all students take calculus, that'll help you remember which functions are positive and which functions are negative. And that'll help you with some of the problems on the assessment. Okay, so we're going to start the review with periodic functions. And you'll notice on the review guide I've indicated which questions are non-calculator. If it doesn't say non-calculator, then that means it is on the calculator section of the test. So if we take a look at this first image, you'll notice that you're given an angle, but it's not really spelled out. You have to do a little bit of work to figure out the value of theta. And the one thing I want you to notice is that that arrow is going clockwise around to form the angle, which is an indication that theta has to be negative. And if I want to find the value of theta, I've got to do a little bit of arithmetic. And there are lots of different ways that you can figure this out. So one of the things you could do is you could figure out what the positive angle is. You could figure out what this value is and then subtract it from 360. So if I know, for example, quadrant 1, this is 90 degrees. So this whole angle here, this green angle, would correspond to a 120-degree angle. And so because these two angles are complements of, or I guess they form the circle, if I did 360 minus 120, that's going to leave me with a 240-degree angle on this side. And I just have to remember that since I'm going the other way around, it's going to be a negative 240. You could also figure it out by just thinking, all right, well, quadrant 4, that's going to correspond to 90 degrees. Quadrant 3 is 90 degrees. And then the remainder of this would be 60 degrees. And 90, 90, and 60 will add to give you a 240 as well. So theta is a negative 240 degrees. And again, that's going to correspond to a positive 120 degrees. In letter B, it says, what ordered pair is associated with theta on the unit circle? Well, we just did that. So if we go back to our unit circle in the previous slide, if I can, that negative 240 or positive 120-degree angle is going to leave me with this ordered pair here. So let me go ahead and write that. It's going to be a negative 1/2 and a positive square root of 3 over 2. And it asks for then the sine of theta. Remember, the sine of theta, if we're looking at the unit circle, is going to correspond to the y-coordinate of that point. So that's going to be the square root of 3 over 2. And the cosine then would correspond to the x-coordinate of the point, and that would be negative 1/2. You may also be asked to find the tangent of theta. The tangent of theta then would be the sine of theta over the cosine of theta. And so in this case, I'd be taking the square root of 3 over 2 and dividing that by a negative 1/2. That's a compound fraction. And so if I want to simplify it, I'm just going to use my rules of division of fractions, and I'm going to multiply by the reciprocal. So I'm going to keep the top fraction the same, and then I'm going to change from division to multiplication, and I'm going to flip the other fraction. I'm going to take the reciprocal, and that's going to be negative 2 over 1. And what's nice about this situation is that these 2's will cancel, and I'm just left with the square root of 3 times negative 1. And that's going to leave me with a negative square root of 3. All right, and number 2, it says to determine the length of an arc, or determine the arc length of a sector with an interior angle of 72 degrees and a diameter of 20 inches. You do have to remember the formula for arc length for this test. And the formula, if you can remember, the arc length is just going to be the radians times the radius. Okay? Now in this case, we're not given the radians. We're given 72 degrees. So the first thing I'm going to need to do is figure out what radians correspond to 72 degrees. And so if you remember from the beginning of the unit, if we're starting off with degrees and I want to change to radians, I'm going to multiply by pi over 180. And this particular question, you'll note, doesn't say non-calculator, so you can use a calculator on this part of the test. So if I pull up my calculator, when I evaluate this, I'm not going to type the pi into my calculator. I'm just going to do 72, and this is just 72 over 1. And if I think about multiplying fractions, this is going to be 72 pi over 180. So if I want to reduce this, I'm just going to type in 72. Oops, let me get on my home screen. I'm going to do 72 divided by 180. And then I'm just going to hit math and then change it to a fraction in lowest terms. And I got 2/5. So 72 pi over 180 is going to reduce to 2 pi over 5. So that gives me my radians. Okay, so if I want to find the arc length, I need my radians, which again is going to be 2 pi over 5. And then I want to multiply that by the radius. Well, in this case, we're given the diameter. And if the diameter is 20 inches, I'm just going to divide that by 2 to get my radius. And so that means my radius must be 10 inches. And again, when I'm multiplying fractions, I can just put a 1 underneath the 10, and I can multiply straight across. So that's going to give me 20 pi over 5. And then I know I can divide 5 into 20, and that's going to give me 4 pi. And the only other thing I have to remember is that I'm measuring a length, and so I have to include my units here. And that's going to be inches. So the answer here is going to be 4 pi inches. So that is one formula you do need to remember, or actually there's a couple things you need to remember. You do need to be able to change your degrees to radians and radians to degrees by either multiplying by pi over 180 or 180 over pi, depending on where you're starting. And then you do need to remember that the length of an arc is found by measuring or by multiplying your radians times the radius. Okay, in question number 3, this question is asking you to match the expressions in column 1 with the expressions in column 2. But in order to do that, you need to evaluate a bunch of different trig functions. So this is where it's really going to help to have a completed unit circle or a unit circle that you can refer to. So before I try to start matching things right away, I'm going to evaluate each one of these expressions. And that's what you're going to want to do on the assessment. If you see the sine of 2 pi, rather than automatically searching for the correct answer, write down what that is equivalent to. It is asking you to find 2 pi on the unit circle. And let's see, we can sort of do that by reconstructing it. 2 pi on the unit circle is right here, and that has the coordinates 1, 0. So if I'm asking you for the sine of that, the sine of 2 pi is just 0. In the next one, it's asking me about the cosine of 45 degrees. Well, 45 degrees is formed here. And again, that's going to be corresponding to my pi over 4 angle. That's the square root of 2 over 2 and the square root of 2 over 2. So if I'm asking for the cosine, I'm looking for the x-coordinate, and so that's going to be the square root of 2 over 2. The cosine of 5 pi over 4, that's another 45-degree angle. I've just got to figure out what quadrant it's in. So we know that this is pi over 4. This angle right here, remember, my numerator would be 1 less. So this is 3 pi over 4. So 5 pi over 4 places me in quadrant 3, where the cosine is negative. So this is going to correspond to a negative square root of 2 over 2. And then the last one asks me to find the cosine of pi. Well, pi is right here, and so the coordinates of that point are going to be -1 and 0. And the cosine then is just going to be -1. So now that I have all those evaluated, I want to go into column 2 and do the same thing. So the sine of 3 pi over 4 is going to correspond to this angle here, and that's going to leave me, again, it's a pi over 4 angle, so this is going to be the square root of 2 over 2, and I know it's positive because the sine is positive in quadrant 2. Letter A is already evaluated, that's why I skipped it. Letter C is referring to the tangent of -180 degrees. So I got to remember, a positive 180, I'm going this way around the unit circle. A negative 180, I'm just going the other way, but I land at the same place. And so the ordered pair associated with that, again, is -1, 0. And the tangent of -180 then is just going to be the y value, which is 0, divided by the x value of -1. And when I divide, I'm just going to get 0. The sine of 270, so 270 degrees, is this point right here, and that's going to correspond to 0, -1. And the sine of that, that's just the y value, is going to be -1. And so what I need to do to answer or to complete this problem is just to match. So in number 1, the sine of 2 pi is 0. That's going to correspond to letter C, the tangent of -180 degrees. And the cosine of 45 degrees, which is square root of 2 over 2, is going to correspond to B, the sine of 3 pi over 4. The cosine of 5 pi over 4 is a negative square root of 2 over 2, and that's letter A. And then the cosine of pi is -1, and that corresponds to the sine of 270 degrees. So that's going to be D. So this problem, you can make it easier on yourself if you evaluate each of the expressions first and then try matching them up. Now, there is not a question that looks just like this on the test, but the skill that is used to answer this question is something that you will come across several times. So make sure that you can evaluate these functions using the unit circle. Okay? In number 4, it says, suppose the tangent of theta is less than 0, and that pi is less than or equal to theta, which is also less than or equal to 2 pi. Another way of saying that is that our angle is between pi and 2 pi, which essentially means it's going to be in the lower half of the unit circle. And we're wondering, in which quadrant does theta lie? This is a non-calculator section. So this is where you really want to think about that. All students take calculus. If I'm telling you that the tangent is less than 0, I'm telling you that the tangent is negative. Well, the all students take calculus is telling me what functions are positive in these quadrants. So I know that in quadrant 1, all of the functions are positive, and in quadrant 3, the tangent is positive. So that must mean that in quadrant 2 and in quadrant 4, the tangent must be negative. So I'm going to put a little check mark there. And then if I look at the second constraint, it tells me that theta has to be between pi and 2 pi. Well, here's pi, and here's 2 pi. So because it's between pi and 2 pi, I'm looking at the lower half of my unit circle. So that tells me that theta must either be in quadrant 3 or quadrant 4. Theta has to lie in the quadrant where both of these constraints are met. And so that's going to correspond to quadrant 4. Okay. All right. Problem number 5 takes a lot more work than a lot of the others because you are still evaluating functions, but this time you don't know where theta is. It's not on the unit circle. If you take a look at the first problem, it says that you're given that the sine of theta is equal to 5 over 13. 5 and 13 are not numbers that are on my unit circle. So I can't just go back to using the unit circle to try to figure out what the cosine is. When you see a problem like this, where the numbers associated with the sine or the cosine or tangent are not on the unit circle, you need to construct a triangle, a right triangle, and you need to refer back to SOHCAHTOA. So when you're going to construct a triangle, it doesn't matter which direction you write it, you want to label your right angle and you want to label what you're calling theta. If I'm telling you that the sine of theta is equal to 5 over 13, you want to think about SOHCAHTOA. Because that fraction that you're given, that 5 over 13, if it corresponds to sine, it's telling you that 5 is your opposite side and 13 is your hypotenuse. And so you have to make sure that you identify where theta is on your triangle so that you know which side is your opposite. You need to identify where your right angle is so you know which side is your hypotenuse. So according to this relationship, 5 is going to be the length of my opposite side, so that's going to be this side here. And my hypotenuse has to be across from the right angle, so that makes this 13. Notice that this is in a non-calculator section of the test. So this requires you to use the Pythagorean theorem to find the length of the missing side. So you need to know your perfect squares. Okay, 13 squared. If you forget how to do that in your head, you're going to have to just multiply it out. There's my 9. I'm going to carry, oops, I don't need to carry the 1. Sorry. 3 times 1 is 3. And then I'm going to drop my 0 and multiply both of those values by 1. So that's 3, that's 1. I get 169. So if I'm thinking about my Pythagorean theorem, if I call this A, and I call this B, and I call this C, then I know 5 squared, which is 25, plus B squared has to be equal to 169. And if I subtract 25 from both sides, I get that B squared is equal to 144. We take the square root of both sides, and that tells me that B is equal to 12. Okay, so that is just the preliminary work that you need to do to set up this problem. Completing the triangle doesn't answer the question at all, because ultimately our goal is to figure out the cosine of theta. Well, I know that the cosine is equivalent to the adjacent side over the hypotenuse. So let's go ahead and do that. The side that is adjacent to theta is 12, and our hypotenuse is 13. But again, I'm not finished because I need to pay attention to the quadrant where theta lies. And if theta lies in the second quadrant, that's this quadrant right here, I know that the cosine in that quadrant is negative. And so that's a lot of work for this problem. It's at least 3 steps. And you need to complete all 3 steps to get to the correct answer. I put another one on there too, just to give you a little bit more practice, because I know on the unit test, this was something that a lot of students got wrong. So I have another one up here as well. So in letter B, you're given that the cosine of theta is equal to negative 16 over 20. So notice that this time you're given a cosine and it gives you a negative value. You can do this a bunch of different ways, but I ignore the negative when I'm setting up my triangle. So if I'm calling this theta and I'm calling this my right angle, cosine this time, the 16 is going to correspond to my adjacent side, and the 20 is going to correspond to my hypotenuse. So my adjacent side is going to be right here. My hypotenuse is going to be 20. And so again, like this is in the non-calculator section, so to figure out the missing side, you have to do your Pythagorean theorem. Well, 20 squared is going to be 400. So basically, if I call this A, and I call this B, and I call this C, I'm looking at A squared plus 16 squared has to equal 20 squared. So A squared, 16 squared is 256, and 20 squared is 400. And when I subtract 256 from both sides, I get that A squared is equal to 144. And when I square root to both sides, I get A equals 12. Okay, so again, that's just the preliminary work that I need to do to set this problem up. Now I'm ultimately trying to find the tangent of theta, and from SOHCAHTOA, if I think about TOA, that means that I'm looking for the opposite side over the adjacent side, which is 16. And then I also have to pay attention to what quadrant theta is in so that I know whether or not I'm going to have a positive or a negative value. And since it's in the third quadrant, that's this quadrant here, I know all students take calculus. I know the tangent is positive in the third quadrant, so I'm just going to leave my answer like that. If you want to put a positive sign, you can. Now, ultimately, you can reduce that fraction. I probably should have given you a problem that had a reduced fraction to begin with, but 12 over 16, if you want to reduce it, you certainly can. Okay. Let's take a look at number 6. Now we're looking at graphing and modeling periodic functions. So in number 6, you're given a graph of a periodic function. And again, a periodic function is just a function that has a cycle that repeats exactly over and over and over again. You're asked to state the equation of the midline. So I'm just going to try to figure out where that is. It looks like it's about right here. And so that makes my midline y equals -2. And then my amplitude, that's just the distance from my max to my midline or my min to my midline. It should be the same value either way. My amplitude is going to be 4. Remember that your amplitude is always a positive number. It does correspond to the a value of your sine or cosine function, but it's always going to, the amplitude itself is a positive number. And then in letter C, it says, what is the length of the period or the cycle? So you'll notice that the x-axis in this case is not marked by values of pi, or it's just marked regularly, -1, +1. But I can still find the period by figuring out how long it takes to complete one cycle. But you want to figure out nice, easy points to calculate where your cycle starts and where it ends. And it's a little bit hard because of the way this graph is shifted. But if, let's say I say my cycle starts here at -2, and if I follow, then I'm looking basically at a negative sign function, so it'll end right here. And so ultimately, I want to figure out this length from beginning to end. And so you can do this a bunch of different ways. I can figure out, like, the distance here is 2 units and the distance here is 4 units. When I add them together, that gives me a distance of 6 units. I could also count each of the notches, and that's also going to tell me that the period in this case is going to be 6 units. Most of the time, your x-axis is measured in radians, so it's going to be some value of pi, but in this case, I didn't scale it that way. All right, in number 7, this is one of your modeling problems. So this is now where we're taking our periodic functions and we're relating them to some real-life situation. So in number 7, it says the volume of traffic at a certain intersection follows a sinusoidal function with a period of 12 hours. So if I'm dealing with a period of 12 hours, I know I'm going to go from 0 to 12. And it says the least amount of traffic occurs at noon with approximately 35 cars traveling through the intersection. So that tells me this 35, if it's the least amount of cars, that's going to be my minimum y value. And then it says it's heaviest at 6 p.m. during rush hour when there's an average of 175 cars. So this number here is going to correspond to my maximum y value. And I'm going to go ahead and mark them on my axes, on my y-axis. So I'm going to let this be 35, and I'm going to let this be 175, and this is going to correspond to the number of cars. And it looks like I'm going to go ahead and label my graph as traffic. My x-axis is going to correspond to time in hours since noon. A lot of times it'll start at midnight, but this time we're looking at the latter part of the afternoon. So it says we're looking at the number of hours since noon. And we're looking over a 12-hour period of time. So I can call this 0 and I can call this 12. This 0 is going to correspond to noon, and this 12 is going to correspond to midnight. Okay, so in here, when I have 6, this is going to be 6 p.m., this will be 3 p.m., and this is going to be 9 p.m. And you do want to make sure that you scale it a little bit. When it comes to constructing the graph, in order to get all of the points for this problem, you need to make sure that you label and scale both axes completely and give your graph a title. You also want to make sure that you mark the maximum and give yourself some tracks as well as the minimum, and that you mark the midline. And to calculate the midline, we essentially find the average of our maximum and minimum. So I'm going to add them up. So that's 110. And then I'm going to divide by 2 to find the average. So if I divide that by 2, I get 55. And so it's important that you also include that midline. And so now I'm going to use the context of the problem to start plotting some points. So I'm going to go back through. It says the least amount of traffic occurs at noon. So the least amount occurs at noon. That's my minimum. So I'm going to put a point at my minimum at noon, which is that 0 hour. And remember, if I'm dealing with a cycle or a period, it's going to begin and end on the same line. So if I'm starting at the minimum, I'm going to end at the minimum. So I can actually plot that last point as well. And then it says it is heaviest at 6 p.m. during rush hour when there's an average of 175. So I know at 6 p.m. I want to plot a point on my maximum. And I can see now, the way this is structured, that this is going to be a negative cosine function. That means it's got to cross the midline at 3 and 9. And you need to make sure that you plot 5 points to get all of the credit for this problem, and then go ahead and sketch your graph. Remember that it's a cycle. It's a periodic function, so you don't want to just draw a parabola, because I think one of the things I was seeing is students just kind of drawing a parabola. You got to remember that this is a cycle that's going to continue to go up and down. So your graph should never go below your minimum or above your maximum. It should look like a periodic function. And so if you've got all of those elements on this problem, you're going to get every point you need. And I believe this is a 3-point problem on the quarterly, and there's a specific rubric that teachers have to follow. So if you miss something, like you forget to put your title or you forgot to label your graph, you're going to lose a point. You're not going to be able to get all 3 points. All right, and number 8, this is another problem where you have where you're modeling using a periodic function, but this one is actually calculator based, and so you're not actually going to need to construct the graph on your paper, but I think it helps to sketch it so you understand what the question is asking. So in number 8, it says when a river flows into an ocean, the depth of the river varies near the mouth as a result of tides. Information about this change in depth is critical for safety, and the following equation gives the depth in feet of the Thames River in London over time, where t equals 0 corresponds to midnight. And so you're given an equation, and in letter A it says to sketch the graph of the situation over a domain of 24 hours. So we're going to go ahead, and I'm just going to sketch this on my paper. So I'm going to go ahead and let 0 correspond to midnight, and then if we're doing this over 24 hours, there's my 24. Okay, so this is time. And we're dealing with the depth. So just to kind of reinforce what you should be doing, we want to do the depth. And one of the things that you're going to need to do if you're going to be graphing this on your calculator is you're going to want to set your window up. So let's think about what we know about this equation before we even move to our calculator. If I want to calculate the maximum value and the minimum value of my function, I've got all that information already in my problem, in my equation. Remember, this value right here is going to be our midline. So I can go ahead and sketch that there. This is going to be 26.26. And if this is my amplitude, to calculate my maximum, I'm just going to add. So on my calculator, I'm just going to do 26.26 plus 7.97, and that gives me a maximum of 34.23. And if I want to do my minimum, I'm going to take my midline, 26.26, and I'll subtract my amplitude of 7.97. And that's going to give me my minimum of 1828. Okay, so now when it comes to completing this problem, in letter B, actually let me go ahead and draw my tracks. In letter B, it says, according to the trig function, what is the average depth of the Thames River? One of the things to keep in mind is that the average depth when you're dealing with a sine or cosine function is just going to be the equation of your midline. And so I don't have to do any math here. I just have to recognize that the average depth is going to be that midline of 26.26 feet. And then in letter C, it says, if a ship requires at least 30 feet of water to navigate the Thames safely, graphically determine the time intervals from when navigation is safe. This is where you're going to have to use your calculator. So when I graph this on my calculator, I'm going to go into y equals. If I have anything in there, I'm going to go ahead and clear it out. Make sure that none of your plots are highlighted so that you know that they're all turned off. And I'm going to go ahead and type in my function. 7.97 times the sine. 0.5. No, I don't have a t on my calculator, so I'll just use x plus 0.035. Close your parentheses, and then add your midline, 26.26. Now, before you start to go graph, the other thing you want to make sure is that your mode is in radians. So if you look at that third line, make sure radians is highlighted and not degrees. Now, I don't know what window I'm set at. It looks like I've got a standard window right now, and so if I go to graph, I don't see anything. And that's because I need to adjust my graph to make it look like what I wrote on my paper. So if I look at my window settings, I know that my time axis, that's going to correspond to my x-axis. I want that to go from 0 to 24. It really doesn't matter what your scale is, so you don't really have to worry about it. In terms of my y-axis, I'm going to keep my y-min at 0. And my y-max, I mean, I certainly could write my y-max as 34.23, but I sometimes like to have a little bit of wiggle room, so I'm going to make my y-max 36. And now when I graph, you should see your function. And what you should notice is that it goes through 2 complete cycles in a 24-hour period of time. So there's 2 high tides and 2 low tides. Now this isn't going to stick up here, so I'm just going to have to sketch. Looks like it starts a little bit above my midline, goes down, up, and back up. Okay? And ultimately, what we want to do is figure out during which time intervals it's safe to navigate. And so if this ship requires 30 feet, if I think 30 feet is probably in here somewhere, if I just look at my paper, I can see that means that this is where the water is deep enough. This is where the water is deep enough. So I need to figure out these time intervals on my x-axis. Let me do it this way. So I need to figure out these values of x. And I can do that using the calc functions on my calculator. Before I do, though, I'm going to go back into my y equals screen, and in y2, I'm going to go ahead and enter the 30 feet. And so now you'll be able to see the 2 intervals from which the ship can actually pass through. So to find those points of intersection, you'll notice you have a trace button on your calculator, and behind it in blue, you'll see the calc. If I hit second calc, I'll give the whole menu. I can find the minimum, the maximum, the zeros of the function where it crosses the x-axis, or I can even find the intersection points. Now I'm going to have to do this 4 different times to figure out each of those 4 points. And you can flip back and forth between your graphs using the up and down arrow. So for me, I'm going to flip up to the horizontal line because it'll be faster for me to get to that first point. And I'm going to go in order. So I'm going to go all the way back to that first point. And once I have my cursor close enough, I'm just going to go ahead and press enter and follow the instructions. It tells me to pick a second curve. You can just keep pressing enter until it says intersection. And so what I can see is that at 0.9 hours, the water is deep enough. So it's going to be between 0.9 hours and let's go ahead and find that other one. I'm going to do the same process again. Second trace, I'm going to choose intersect. And this time I'm going to scoot and find that second point. And I'm going to press enter. You essentially are going to press it 3 times until it says intersection. And that's going to be 5.2 hours. So between 0.9 and 5.2 hours. And then again, between, all right, now I want to find those other 2 points. So I'm going to hit second, trace, intersect. And again, I'm going to move my cursor to the next point. Okay, as soon as I get it close, I'm going to hit enter 3 times until it says intersect. That'll end up being, it looks like it's going to round to 13.5. And then the last point, and we get 17.8. So there's 2 intervals. It looks like once in the morning and once in the evening when the water is deep enough for the ship to pass. Okay, so I think that wraps up our review of periodic functions for the quarterly. And the next few questions relate more to just general characteristics about functions and then more specifically about rational and radical expressions. So for example, expressions that have rational exponents or fractional exponents, and also radical expressions, those that involve like a square root or a cube root. So let's take a look at these two root functions. These are the graphs of, or these are the equations of the parent functions. In letter A, we're looking at the square root of x, and in letter B, we're looking at the cube root of x. And remember that this can be expressed this way as well with a rational exponent. Rational just means fractional. So if I take a look at the first graph, basically what you're asked to do in this problem, you're given the equation of each parent function, and it says to write an equation for the function in the graph. So the function in the graph has been transformed. If I can think about what the graph of the parent function looks like for the square root of x, it has a starting point at 0, 0, and it's that half of a parabola on its side. Now in this case, you don't have to worry about the dilation. It tells you that the value of a is either going to be positive 1 or negative 1. If I think about the transformed equation, it's going to be y equals, actually let me give myself a little bit more space here. The transformed equation is going to involve the a, the h, and the k. So it's going to look more like this, where there's an x minus h underneath the square root and then a plus k on the outside. So the first thing I want to do is figure out the values of a, h, and k. Well, I can see that this function has been reflected, which tells me that the value of a must be negative 1. Since this is decreasing, I know the value the graph has been reflected, so my a value must be negative 1. I'm still going to keep the square root. I'm still going to have the x. But now I need to figure out h and I need to figure out k. Well, this graph has been transformed. It's been shifted back 2 and up 4. So back 2 and up 4. The other thing you can do is just simply find that starting point right here. And the coordinates of that point are negative 2, positive 4. And those are actually going to correspond to your h and k values. But you do need to remember that when it comes to the h value and that quantity that's going to be in the parentheses or under the square root or under the radical, it's x minus h. So if I tell you that h is a negative 2, you have to remember to take the opposite of it. Because x minus a negative 2 is really x plus 2. And then the k value is just going to be positive 4. You don't have to change that. When it comes to letter B, now we're looking at a cube root. And again, my value of a is either going to be positive 1 or negative 1. Since this graph is increasing, I know that my value of a is positive 1. So I'm looking at the transformed equation that's going to look like this. And so I can tell again that a is going to be a positive 1. And then to figure out the values of h and k, I'm just going to find this point of inflection right here. This is where the graph changes concavity. So this side of the graph, it looks like it's curved up, and this side of the graph, it's curved down. So a point of inflection is where the graph changes its concavity. And if I look at this point, I can see the ordered pair associated with it is 1, negative 3. And again, that's just going to correspond to your h and your k values. The graph has been shifted to the right 1 unit and down 3. And so if my h value is 1, then underneath my square root is going to become x minus 1. And then on the outside, I've got plus k. Well, k is a negative 3, so I can either write plus a negative 3 or simply write minus 3. And those would be the two equations associated with these two graphs. Okay, problem number 10. You are asked to identify characteristics of functions that are presented either as an equation or as a graph. And one of the things that I will tell you is that when you see an equation, you really need to get in the habit of visualizing what this thing looks like. So for example, when I look at the first one, I've got 3 times the sine of x minus 5 pi over 6 plus 1. In my head, I want to start thinking about what that graph would look like. I'm actually going to, okay, I just adjusted my screen so I actually have a little bit of space to draw a picture. So let me think about this first graph. It's a sine function. I can see that my midline is going to be at positive 1, so I'm going to draw my midline, and I've got an amplitude of 3, which means that it's going to go up 3 to 4, and it's going to go down 3 to negative 2. So I can see that my function is going to cross the x-axis. I'm not even really concerned about how it shifted left or right based on the questions that I'm asked, because it's just asking me about the domain and the range. But if I were to shift this graph, I'm going to be shifting it to the right 5 pi over 6. And so I can kind of see that it's going to go like this. And it's going to keep going forever and ever and ever. That's why it's called a periodic function. It keeps repeating. So when I'm thinking about my domain, the domain of any of our periodic functions, for at least the sine and the cosine, are going to be all real numbers. The range, though, the range is corresponding, so that the domain corresponds to x, my range corresponds to y. My y values are trapped between my minimum and my maximum, so I do need to think about what they were. Well, we said that our midline was at 1, and if I add 3, that's going to give me a maximum of 4. If I subtract 3, that gives me a minimum of -2. So all my y values are going to flip between -2 and +4. They're just going to go back and forth and back and forth and back and forth. So if I wanted to write my range, there are a couple of different ways that we can express this. We can express it as an inequality, and I would use less than or equal to symbols, and I'd say that y is between -2 and +4. We can also use interval notation, which is just going to be, from -2 to +4. And since y can actually equal those endpoints, I would use a solid bracket. For those of you that are in the standard level class, you don't need to know that interval notation, but for those of you that are in honors, you do. All real numbers, let me actually do that in interval notation as well. All real numbers would just go from -infinity to +infinity. And because x can't actually equal, -infinity and +infinity aren't actually numbers, so I can't use the brackets. I would use just the parentheses to indicate those intervals. And if you think about what a zero of a function is just your x-intercepts. If it's real, it's going to be an x-intercept. And when we're talking about the distinct ones, I'm not talking about duplicates. So like you'll remember with polynomials, we could have double or triple roots. I'm looking at how many times it actually crosses the x-axis. Because this is a periodic function, it's going to be infinitely many. Okay, but some periodic functions won't cross the x-axis at all. Imagine if my midline was at like 6 and my amplitude was only 1. Like, it's possible to have a periodic function that doesn't cross the x-axis at all. And so in that case, it would be no real zeros. It wouldn't cross at all. Let's take a look at the next one. The next one is a square root function. And so I know that it's going to have this kind of characteristic where it's like half a parabola on its side. I can identify the values of h and k. In this case, it's going to be a +4, 2. So if I were graphing this, I'm going to find 4. So 1, 2, 3, 4. I'm going to go up 2. And it's going to look like that. And I'm actually going to go ahead and write the ordered pair 4, 2. So if I'm thinking about my domain, notice that all my x values are greater than 4. So, and actually they could equal 4. So using my inequality notation, I would say that x is greater than or equal to 4. If I were using the interval notation, it would be 4 to infinity. I'd have a solid bracket here and the parentheses here. In terms of my range, all my y values are greater than or equal to 2. Or if I were using the set notation, it would be from 2 to infinity. And again, I'm going to have a solid bracket at the 2 because of the equal sign, and then the parentheses at infinity. And when you're asked how many times can the graph cross the y-axis, how many distinct real zeros are there, this graph never crosses the the x-axis. It doesn't cross the y-axis either. But in this case, there are no real zeros, so there are none here. So that's why it's really important to kind of like get a sense of the graph before you try to answer these questions. So if I take a look at letter H, this is now an odd power. Notice this is a power. And so I've got to think about what that graph looks like. This graph is going to be that S-shaped graph that that increases and decreases vertically. The odd root is the one that looks like the S shape from side to side. When I'm graphing this, again, I want to figure out the values of h and k. H in this case, remember, we're going to take the opposite. It's going to be -1. K is also -1. So if I were graphing this, I need to go ahead and plot that point at -1, -1, which is going to be down here. And I'm going to draw my graph. It's going to be that S shape going up and down. The nice thing about odd roots and odd powers is the domain and the range for both of them are always going to be all real numbers. So you don't have to worry about anything tricky with those. It's just going to be all real numbers and all real numbers. And an odd power and an odd root will only cross the x-axis one time. When we take a look at the next one, this is negative x squared plus 2. Well, x squared, that means we're dealing with an even power, or a quadratic, if you want to think of it that way. My h value in this case, since there's nothing associated with x in the parentheses, my h value would be 0, and my k value would be 2. But I got to notice that in this case, my leading coefficient, that a value, is negative. So I'm looking basically at a parabola that's going to open down with a vertex at 0, 2. It's going to look like that. With parabolas, my domain is going to be all real numbers, but the range is going to be impacted by the vertex. And in this case, since my vertex is a maximum, all of my y values are going to be less than that. And so all of my y values are going to be less than or equal to 2. If I'm using set notation, it would go from negative infinity to positive 2. I'm going to have a solid bracket around the 2, and then the soft parentheses around the negative infinity, for those of you that are in honors. When it comes to the number of times it crosses the x-axis, I can see that it crosses twice. And it's important, too, to think about parabolas, because we have situations where they might cross one time, and we have situations where they may not cross at all. So it's important that you envision the graph or sketch the graph on your paper. And I do want to just reiterate that this question is on the non-calculator section of the test. So you do have to be able to do this without a calculator. The last one I've given to you is given to you in graphic form. And hopefully you guys recognize this. This is a polynomial function. And a polynomial is basically a sum of power functions that are added together. So x to the third plus x to the second plus x minus 1 or something like that. We're used to seeing it in factored form. So for example, like this has an x-intercept at negative 4, so the factor associated with it would be x plus 4. This x-intercept is at negative 1, so I'd have an I'd have a factor at x plus 1. And then I've got an x-intercept here at 2, so this would look like x minus 2. The only thing is, these first two x-intercepts look a little bit different than this third one. And that's because the graph passes straight through with the first two, and it bounces with the last one. In a situation like this, where the graph turns around, it tells me it's a double root. And so that's going to affect my equation, because that factor, let me actually draw the arrow over here, that factor should have a power of 2. So this is what I would consider a 4th degree polynomial. So it is important that you recognize the relationship, that even though this is from last marking period, it's fair game for this assessment. And so in terms of the domain, x can be anything. I can plug in any number I want for x, so x can be anything. But when I look at the graph, if I'm looking at the range, if I'm looking at the values of y, I can see that the lowest point on the graph is right here, and that occurs 1, 2, 3, 4. It looks like it occurs when y is negative 5. All of the rest of this function is above that point. So even though we didn't really talk about the domain and range of a polynomial, from the graph you can see that our y values are all greater than or equal to negative 5. And if I were using the set notation, I would be going from negative 5 to positive infinity. This would be a bracket, this would be a parentheses. And when I'm looking at how many times it crosses the x-axis, and what I mean by distinct is I'm not going to really worry about the double or triple roots. I'm just looking at how many times does it hit the x-axis. And I can see that it hits the x-axis 3 times. And so the purpose of this exercise really is to reinforce the graphs of the functions without you actually getting points for graphing. And being able to identify the domain, the range, and understand what the roots are for the function. And again, those real zeros, the roots of the function, those are your x-intercepts. Okay, we've got 2 more questions to go, and these are more with properties of exponents and simplifying radical expressions. With number 11, we're looking at rational exponents. So you have that 2/3 exponent. You're looking at at a product where I've got 8 times x to the 9th times y to the 6th, and that whole product is being raised to the 2/3 power. So when I have a situation like that, that basically means I can distribute that power to each term. So I'm looking at 8 to the 2/3, I'm looking at x to the 9th to the 2/3, and I'm looking at y to the 6th to the 2/3. And so once I've simplified it there, I'm going to take a look at each term in that expression. So 8 to the 2/3. This is where it really helps to know that 8 is a perfect power of 3. And if I take the cube root of 8, I get 2. And so it really will help to have those powers memorized, at least the first 10. And so when you're dealing with a rational exponent and you're dealing with numbers, you want to take the root first. That's going to be easier. You want to get the number smaller before raising it to the power. So 2 is the power, 3 is the root. I'm going to take the third root of 8 first. That gives me 2, and then I'm going to square it. And so 2 squared is going to give me 4. Once I'm dealing with the variables, I can just use the properties. So a power to a power means I'm going to multiply those two exponents. And again, this is the non-calculator part of the test, so it is important that you remember not only your rules for exponents, but how to multiply fractions and add fractions. So in the first one, I need to multiply 9 times 2/3. So 9 times 2/3, if I think of it as 9 over 1 times 2/3, the nice thing about multiplying fractions is I can reduce. So you can either multiply straight across and then reduce, so in this case it would be 18/3, which is just 6, or you can reduce first. So if I reduced the 3 and the 9, I'd be left with 3 times 2. Either way, that's going to be 6. So that leaves me with x to the 6th power. I need to do the same thing with my y, so I'm looking at 6 times 2/3. Well, again, 6 is just a whole number, so I can put a 1 underneath. I'm going to go ahead and simplify first this time. So the 3 and the 6, I'm going to reduce the 3, and the 6 is going to become a 2. So when I multiply across the top, I get 4. So I'm going to be left with y to the 4th. And that's really all I can do. That simplifies the expression. When I'm dealing with something in letter B, where I'm looking at the 4th root, the other way of looking at this would be to say, okay, this is 81 to the 1/4. Because remember, a 4th root is just a fractional exponent with the root in the denominator. This is going to be x to the 8th to the 1/4. And this is going to be y to the 3rd to the 1/4. And so when I simplify it, again, 81 is a perfect power of 4. It's like taking the square root of a number twice when you take the 4th root of it. So the square root of 81 is going to be 9. When I take the square root again, I'm going to get 3. When I'm dealing with the next term, I need to multiply 8 times 1/4. So 8 times 1/4, again, that's going to be 8 over 1. The 4 is going to cancel with the 8, and I'm just going to be left with 2. So this is going to be x squared. And then y, when I multiply 3 times 1/4, I'm just going to be left with 3/4. And I can't really simplify that any further. So for those of you that have the standard test, you can leave your answer like this. For those of you that have the honors, that are in honors, you will have to leave your answer in radical form. And so one of the things you'll have to remember is that this expression can actually be written in radical notation. So the 3x squared is still going to stick around on the outside. But you're still going to have the 4th root of y to the 3rd. That really can't be simplified any further. So you would leave your answer in that notation. In letter C and D, you're adding radical expressions. In letter C, the two expressions are the same. So we've got 3 square roots of 2 plus another 5 square roots of 2. Since these two quantities are the same, I can add them together. So if I have 3 square roots of 2 and I give you another 5 square roots of 2, that means you have 8 square roots of 2. But in letter D, I cannot combine the 8 and the 18 because those two expressions are not the same. They have to be the same. But if I think about it, if I'm dealing with a square root and I think about the number 8, there is a perfect square that is a factor of 8. If I think of 8 as 4 times 2, and if I think of 18 as 9 times 2, let's just take it one step at a time. I can take the square root of both of these numbers, right? The square root of 4 is going to be 2, and I'm going to still be left with the square root of 2. If I separate the square roots in the second part, I'm going to have the square root of 9, which is 3, and I can't really do anything with the square root of 2. Once I simplify both expressions, they both involve the square root of 2. So I've got 2 square roots of 2 plus another 3 square roots of 2, which leaves me with 5 square roots of 2. So you do need to be able to add those. And then finally, in number 12, we're dealing with inverse functions. In letter A, you're given that y is equal to x squared minus 1. And all this is telling you right now is that the domain is restricted, because if you think about a quadratic function, that's what this is. It's an even power. If I think about x squared minus 1 is going to be a parabola that looks like this. If I were to take the inverse, it's going to be a parabola that looks like this, and the inverse wouldn't be a function. So all this is telling me is that I'm only looking at the positive values. So I'm not going to look at the lower half of the inverse, and that's going to make it a function. So you don't really have to do anything different when it comes to that restricted domain. Let's go ahead and do the process. Our first step is to switch x and y. So this is going to become x equals y squared minus 1. My next step is to solve for y. So I'm going to add 1 to both sides, and I get x plus 1 is equal to y squared. Now typically, when we take the square root of both sides, I include the plus or minus symbol. The fact that I've restricted the domain here is telling me that I'm only interested in the positive root. So I don't have to include that plus or minus symbol. I'm just going to be dealing with the positive square root of x plus 1. And the whole reason that we use the square root is because it is the inverse of the square. So the square and the square root are going to cancel, and I'm going to be left with y is equal to the square root of x plus 1. But I do need to make sure that I'm naming this function something other than what I started with, because they're not the same function. So I use my inverse notation. And so this is called y inverse is equal to the square root of x plus 1. In letter B, now I'm dealing with a cube root of x plus 2 minus 3. And this time I'm using function notation, so I'm calling this f of x. But that's still the same thing as y. So this y equals the cube root of x plus 2 minus 3, that's the same thing. I'm just calling it f of x instead of y, but it's the same thing. So our first step is going to be the same as it was before. I'm going to switch my x and y's, and then I want to solve for y. So essentially, I want to get the cube root by itself, and then I'm going to undo the cube root with a power. So my first step is going to be to add 3 to both sides. So I'm going to have x plus 3 is equal to the cube root of y plus 2. And while it may be tempting to subtract the 2, I can't do that yet. Now I want to undo the root by raising it to the power of 3. And I'm going to raise that to the power of 3. And so the root of 3 and the power of 3 are going to cancel, and I'm just going to have y plus 2 is equal to. Now in this case, even though it might be tempting, I can't distribute that power of 3 because I'm dealing with addition. If it was 3 times x, I could cube both things, but with addition and subtraction, I can't distribute the power. So I'm just going to leave it as x plus 3, the quantity cubed. And to finish solving for y, I will subtract 2. And again, I can't combine the 2 with the 3 inside the parentheses because it's inside the parentheses. It's kind of trapped. And this is going to be equal to y. But again, I don't want to call it the same y that I started with. I'm going to want to call it y inverse. And actually, since my function was originally called f of x, I'm going to want to call this f inverse of x. If you were asked about the domain and range, you just want to remember that the range of the inverse is going to be equivalent to the domain of the original function, and vice versa. So when you take an inverse of the function, it is going to just switch the domain and the range. The domain becomes the range becomes the domain. So I hope that's helpful. Obviously, you can come and see your teacher if you have any questions. Good luck. We hope you guys do well on this.